I'd like to begin also thanking the organizers of the workshop, GSM 2022, for putting this wonderful workshop together in this particularly difficult time. Also, I thank the audience for still sticking around. So before I go to introduction, I'd like to acknowledge the contribution from my grad students in my group called the YOUNG, standing for Yonsei Observable Universe Group. In particular, the work that I'm presenting today is part of the PhD thesis by Jenny Kim, who graduated this year and is now a postdoc at Oxford University. Because the audience has such a broad spectrum of interest, probably it's not too bad why we need to study high-energy galaxy clusters in terms of cosmology. So galaxy clusters are the largest gravitationally bound objects in the universe. As such, they have been used to quantify the matter content of the universe. So if you examine the abundance in the local universe, you can obtain this elongated banana. The reason why we have this elongated banana is the abundance is function of two parameters. One is matter density, and the second is the power spectrum normalization. However, if you add sample from the high G, you can break the degeneracy, and you can tremendously shrink the size of the banana, and you can enable the precision cosmology. Also, sometimes when you find very unusual galaxy cluster, very mass cluster, that can rule out certain cosmologies. So this is a little bit old, but very important result by Bacall and Fan in the year 1998. So y-axis is the abundance of galaxy cluster as a function of redshift. At the time, there was a cluster called MS1054 at redshift 0.8. Given the mass, that existence cannot be reconciled with the matter-dominated universe. So this is pretty remarkable because 1998 is a few years before people talk about dark energy from the supernovae observation. And sometimes extremely massive clusters at extremely high redshift can be a good sanity check whether or not lambda CDM is the most feasible model. So here we can see what we call the exclusion curve. That means if you have a cluster mass that lies above this line, then there should be some trouble with our lambda CDM. So fortunately, in this case, there's no serious tension given by these high-redshift clusters. But when you have more high-redshift samples, it's certainly something you can test to check our lambda CDM model. Oops. Okay, so to enjoy such a game with the high-redshift clusters, the most important thing is, of course, the mass, exact accurate mass of the cluster. As you know, well, there are several pathways to the mass. One can use the richness, loss dispersion, Sunyaev-Zeldovich effect, luminosity, also temperature from the X-rays. But as you know that clusters at high G, they are like teenagers, they are never relaxed. You cannot assume hydrostatic equilibrium. So that means they are not useless, but they need to be calibrated with a proper tool. And here I'm claiming that gravitational lensing is the most useful tool to calibrate those massive boxes. So here's one example of a fantastic job by Kim Sharek et al. 2021. X-axis is redshift, y-axis is Sunyaev-Zeldovich detection significance. So you can tell the relation changes as a function of redshift. So next I'm going to talk about our cluster sample and the data we used. We used 42 galaxy clusters from redshift between 0.8 and 1.8. And that distribution is shown by this solid histogram. They come from many different surveys: optical, near-infrared, X-ray, and Sunyaev-Zeldovich surveys. And 42 is a pretty large photo cluster sample. And the sample size is comparable to the largest ground-based programs such as CCCP, Ring the Giant program, and the Locus, etc. Okay, just for the record, this is the list of our 42 clusters, and let me know the list include your favorite target. Ranging can be measured by imaging data, but interpretation is enabled by high-quality spectroscopic survey data. That's where Gemini spectral data contribute. So we utilize the published spectroscopic catalogs as well as our own Gemini data obtained by KGMT program. They allow us to map the galaxy distribution in the clusters, and they allow us to also select the source galaxies. And we can do contamination analysis for the source selection. And finally, they provide velocity dispersion, which is one of the useful mass proxies. Then I will just quickly summarize some of the important systematics. So as you all probably have heard of, with great statistical power comes with great systematics control responsibilities. So I'm going to quote a few systematics that may matter to you. First, I like to say cluster ranging at high G is very difficult. So in this image, I want to challenge you to find galaxy clusters. Of course, there's a very obvious one. That's a Lynx nose, but the ratio of the cluster is about 0.6. The mass is 2 times 10 to the 14 solar mass. It's not particularly a massive cluster, but its presence is undeniable. But here, there are 2 more clusters at least at G equal 1.2. If I ask you to find that, probably you have to scratch your head. Here is Lynx East at G equal 1.22. Another one, which is the other one, is Lynx West at G equal 1.23. So they are really tiny, and just looking at how thin they are, how small they are, you can sort of imagine how difficult it is to do lensing for those high G galaxy clusters. So they are distant, that means by geometry, the lensing efficiency drops by a factor of 4 in this particular case. And they are small, that means the source density per physical area drops. Here, it's a roughly factor of 10 difference. And you have to rely on galaxies behind these faint galaxies. That means measurement noise increases by another factor of 2. On top of that, clusters grow with time, so you're looking at smaller child galaxy clusters. That means their masses are on average smaller, so lensing signal to noise ratio drops by the same factor. So this is Lynx East that I showed in the previous image. And here comes HST. And without saying too much, you can tell the advantage of using high resolution images for lensing. So here, let's look at this galaxy here. The same galaxy appears very round. Here it's stretched because of lensing, but it looks round because of the PSF. However, if you do a lensing for high-G galaxies, you can ask the same question to the galaxy here that looks very round. But HST PSF is also finite, and that galaxy can be smeared by HST PSF that looks rounder. That means you still have to care for the PSF modeling. PSF modeling is pretty challenging because HST orbits around the Earth every 98 minutes. Depending on its location, the temperature changes. That means focus value changes. Depending on the focus, your PSF pattern changes. So if you do not correct for the PSF, every galaxy you detect will be stretched along that line. They can masquerade as false gravitational lensing signal. The good news is that it orbits around the Earth every 98 minutes. That means if you know when and where the observation is taken, you can predict the knowledge of the PSF as a function of the location. Knowing PSF is one thing, but measuring shape is quite another, because galaxies do not have a simple morphology, especially at high G. They have very different radial profiles. They have come with their own intrinsic electricities. So you cannot drive the relation between measured electricity and the shear. The only thing you can do is run a bunch of numerical image simulations and calibrate it. So, for example, here is input shear, and here is output shear, and the departure of the slope from the unity is a measure of your bias. The eco-ranging community realized the importance of this test, and they held the so-called shear testing challenging program on a regular basis. And last such challenge happened in the year 2015, and our team participated in the challenge and actually won the challenge. So here I can tell you that at least shear systematic is concerned, we are good up to less than 0.1%. The next systematic comes from the spherical curve. Galaxy clusters are never spherical, especially at G greater than 1, but we assume that they are spherical, meaning that we fit inevitable profile, whatever it looks like. So this is a Marble bias. Fortunately, there's a way to address this Marble bias, because we can also measure the projected mass without assuming any projected parametric form of the cluster density profile. Y-axis is the parametric approach, and again, the slope indicates how much Marble bias matters. Given the statistical scatter, currently, we believe that Marble bias is consistent with 1. Okay, so with these tools, we went ahead and measured the masses of all 42 high-G galaxy clusters. And every cluster is a precious baby, and each one deserves 1 hour talk. But for the sake of time, I'm going to just highlight 2 of the most interesting clusters, also present the summary statistics. The first cluster that I want to talk about is this cluster, which has a 2106 minus 5844. The cluster was actually detected by initial SPT survey and looks pretty much round. At the time, the cluster mass was inferred to be 2 times 10 to 15 solar mass. So that's enormous mass. It's like a 100 kilogram baby, at 3-year-old. But given the redshift, probably the hydroscopic equilibrium assumption could have caused the bias. So you must do the analysis with the lensing and show the error obtained recognition analysis from the HSD data. It looks pretty round, consistent with the round shape seen by SZ. But our lensing analysis based on the initial HST and our near-infrared imaging data allow us to resolve 3 substructures. You may say, how come do you believe those substructures are real? Well, here comes again the role of Gemini spectroscopic data, because we can map out the cross-galaxy distribution, and they support the 3 substructures we found from the lensing. Later, we did a follow-up study with the ALMA. Actually, this is a Synergy observation from the ALMA, and the ALMA found 2 significant peaks corresponding to the north and the southern peak for this galaxy cluster. So the mass that we obtained is consistent with the previous SG result, but still lower than the initial X-ray based measurement. The expected abundance of this cluster is about 1.3 from the 25,000 square degree. That means the probability is about 70%. So it actually does not challenge our lambda CDM. The other interesting cluster is cluster at G 1.8. So this is the highest redshift ever measured with the lensing. And you can tell this is the diffuse emission from the Chandra. Our lensing analysis show that actually this might be a merging cluster, consists of 2 mass clumps. The northern clump's mass is about 5 times 10 to 14, and the southern cluster is similarly 4 times 10 to the 14 solar mass. So if you confirm it, it can be very interesting merging cluster at G equal 1.8. The curious thing is, if you add two masses together, it's almost 10 to the 15 solar mass. 10 to the 15 at G equal almost 2. That's pretty, big mass. However, the caveat is that the mass uncertainty is large, about 30%. So now is not the best time to claim that we have, lambda CDM is in trouble, so it's worth pursuing, keep refining the precision of the mass measurement based on deeper observations. Okay, so here is again the exclusion curve. Here we plot every cluster we measured with big ranging, and you can tell some extreme mass clusters, they may have some boundary issues with the lambda CDM. But again, given the size of the error bars, we cannot claim that anything really seriously challenges the lambda CDM. We still have to wait and see when we shrink the error bar considerably. Another important statistic that we can come up out of the 32 Gauss process is so-called the scaling relation. So here, E is Hubble parameter, and this is mass, normalization, X-ray temperature, and alpha is the slope. If Gauss clusters are self-similar, the expected slope should be 3 halves, 1.5. And this is our result. So the solid black line is our linear regression from the sample that we analyzed. And the green line here is the same kind of weak ranging study done by Henk Hoekstra, but for much low ratio to sample. And here, we find that actually the relation is very similar between the low Z and high Z. And normally consistency is good, but here I'm not too comfortable with the consistency because at G greater than 1, probably the degree of hydroscopic equilibrium or departure from the hydroscopic equilibrium should be different from the one in low G. So that's something interesting. And the last summary statistic I want to show is the mass concentration relation. Concentration parameter is defined by the virial radius of the cluster divided by the scale radius. Numerical simulations show that as you increase the mass of the cluster, concentration value drops. However, recent theoretical studies predict that if you go high ratio, actually the correlation disappears, and at the extreme end, massive end, actually it shows upturn. That has been considered remarkable and well accepted in the lensing also cluster community. But our observation shows that actually the mass concentration relation still shows a negative slope consistent with the prediction at the low G ratio. Mass concentration relation is very sensitive to cosmological parameters, or also the shape of the power spectrum. So the difference between the observation and the theory is pretty significant and also interesting. But again, this is not the best time to question the lambda CDM because the simulation, embodied simulation, we know that they are not complete. The baryon physics, Asian feedback, stellar feedback, they are all implemented through so-called questionable subgrid physics. So unless we are at the stage to implement the baryon physics, it's too early to call this discrepancy as a problem for the lambda CDM. So here is my summary. While you are reading it, I will take a question. Thank you.
Thank you very much for that wonderful talk again. Questions? And while people are thinking, I have one to ask. So you were mentioning reducing the error bars in the mass measurements. So, going forward, what are the methods you could use to reduce the error bar and get tighter mask constraint with weak lensing?
So the currency in lensing is the source density. Usually we are talking about 100 galaxies per square arc minute. The depth will increase if you increase the depth of the observation. So the normal typical orbits that we use is about 5 orbits per filter. So if you increase that, probably we can have 150, even 200 galaxies per square arc minute. That will shrink the statistical error significantly. Also, Gemini observation will help. Here, we still rely on the broadband photometry to select the background galaxies, but inevitably, that will include the foreground, also the cluster members. But the Gemini spectroscopic data will give us better knowledge of the optimal color range, also the magnitude, the range to increase the purity of the background galaxies.
Well, I'll ask a question. I think this is on if you can hear me. Great talk, James. It was
Thank you.
very, very good talk. How do you account for the lensing signal along the line of sight? These are galaxy clusters above redshift 1. And of course, there's lensing all the way along that line of sight. How do you allow for that in your estimates of the masses?
Yeah, that's very good point. For every landing talk, you can ask that question and challenge the speaker. That's a concern if you have low G galaxy clusters, because high G galaxy clusters are harder to find, right? So that's a concern if you do lensing analysis for the low G clusters. But for high G galaxy clusters, if there's a low G foreground, it should be very obvious, right? Your spectroscopy survey or the optical image will tell the presence of those low G interlopers. Of course, the situation will change if there's even higher ratio, like a G equal 2 or higher, then there's nothing we can do very much.
Okay, thank you.
I had one last question. Obviously, collecting area and angular resolution is really important. Do you think there's hope of using adaptive optics to?
Definitely, yeah. So GMOS, I learned how to pronounce that instrument in this workshop. The GMOS will be a fantastic job. The field of view is not optimal, but that works for high G clusters because the angular extent is a little bit larger than 1 arc minute by 1 arc minute. So if you have a 2 arc minute by 2 arc minute field of view and have a Fourier transform of like 1.1 arc second, I think it would, do a fantastic job.
Right. I guess the other piece that's going to be challenging is the point spread function and its stability across the field.
Of course, yeah. Position dependent point function. How nasty that variation may be, that's actually the key question.
Okay, let's thank James again.